I will be talking about the renewable power integration with the grid. And today, power sector is buzzing and it's the main happening sector. And among the power sector, we have RE as the uh, major, you can say, sector which is in focus today and growing continuously for last many years and has another more than last many years to grow further. So the growth is tremendous. We had set a target of 500 gigawatt by 2030, and we already have 280 gigawatt is already installed. And by 2050, the target is about 1,800 gigawatt. And we started in the right time. And because of that, we are getting the benefits of this right start of the this energy of renewable. Today, our energy security has increased because of this renewable penetration in the system. The content of renewable is increasing very fast, and particularly, as also you mentioned, the world situation is very volatile, and this gives us enhanced energy security. And we have to reduce our dependence on fossil fuels, which are subject to a lot of uh, issues, not only environmental, but even availability, as we have seen recently. And we have to just see that we maintain the pace what we have started about the renewable power. And we don't falter on the execution part. The planning is perfect. The regulations are in place. And the execution has to be perfect to deliver the things to the right, you can say, point. Because recently we have seen certain failures. Maybe they have to be taken care. We'll discuss further also when we go along. What happens is the RE generation is concentrated mainly in the remote locations. And these remote locations, there are certain issues. The grid is weak. The inertia of the grid is very low. The SCR ratios are low. And whenever there is a fault occurring in the system, in this weak grid system, the system is not able to save itself from total isolation. What is happening is the fault is not cleared in time. There is no energy to feed the fault and clear it. The inertia is low. It is not able to hang along for longer time. And things are not what is expected of the system, because what we have so far seen is the thermal plants, oil plants, and the stable plants. They have big inertia. They have synchronous generators running, and they are able to feed reactive energy whenever it is required urgently, and they are able to maintain the continuity. Whereas in RE plants, the continuity is an issue, and that has to be tackled, and it is being taken care. What is happening is CEA has formulated guidelines, and they have mandated that 33% of the installed capacity has to be dynamic reactive compensation. Means this dynamic compensation is available with all the RE plants today. And whenever there is a fault, these SVGs, we call them, or STATCOMs, they respond within 5 milliseconds and they supply the reactive power required for the system. They are able to overcome LVRT, HVRT situations, and they are able to save the plant, and continuity is being maintained. So this is what has already been put in practice. And further to that, because these SVGs are in fact aiding the grid inverters, because grid inverters also during these fault conditions, they go into reactive power mode. They also try to maintain the voltage, and they are helped by the SVGs, which are also mandatory now and they are available. And both put together, they are able to see the situation is maintained. And taking this uh, renewable power from remote locations to the main load centers, which are far away in the developed areas or in the mainstream areas, is a big task. And for that, transmission systems are also being added equivalently. And there is massive investment on the transmission system also. Infrastructure is coming up. And because of that, we are able to see that we utilize this. The evacuation is happening because so far there has been a gap. The RE generation is there, but the pace of transmission has not been developed at the same pace. And there has been, you can say, gap between these two. So that is being taken care now. And the government is already considering China type super grid where HVDC links and HVAC lines, power lines, will be taken up, will be installed. And to cater to this, you can say, taking energy from RE places, remote places to the mainstream, and then interconnecting with the state grids and the interstate grids and all. And here, central and state agencies both have to work in coordination. There are WRLDCs there, they are doing a big job, good job. There is a Central Transmission Utility of India. There is a CEA is there, Grid India is there. So these people are ensuring that initial commissioning is done as per the standards set by CEA, and they are in line with the international requirements. And there are simulation studies done before the commissioning is allowed, and this is being followed religiously, and things are going right in so far as the simulation and the um, requirements, they are being met as per the standards. The only thing is still we feel at ground level there are failures. Although everything seems to be okay when we are simulating, but we find that at the ground level the things are not as good as they should be when we simulate. So that gap has to be also taken care. And there comes the real part, means we have to have the uh, proper selection of equipment. Uh, Here we have dozens of inverters, a variety of inverters available. I don't know how much seriously they are being approved and all. But what we see in Australia, there is just one inverter which is approved for such critical loads. Like they are, as I said, remote areas, very low SCR ratios and all. So every inverter is not able to manage these type of situations. So they have one or maybe another second inverter which is proven and which works. But here we have dozens of them, and I don't know how many work properly and how many are just uh, there for the namesake only. So this approval process and the continuous performance has to be there, and we have to filter out what is working and what is not working, and this has to be there. Otherwise, such a big aim, such a big investment will have issues. And for strengthening the inertia of the system, we have two, three options available. One is that the new plants which are coming, RE plants, they are coming along with grid forming inverters. The battery storage is there. So they have a capacity to sustain the fault conditions in a better way, like conventional plants also. So because they have their own energy available and they can supply reactive power from that and they can clear the fault in time. And what we have seen is there are many thermal plants going out of service and they are just lying idle. So some of the plants, they can be utilized as synchronous generators, synchronous converters, because the same infrastructure is there. We need not generate anything from them, but we can use these facilities and convert these plants into only synchronous converters so that we have the reactive power support and we improve the grid strength and grid stability with these things. So this is another point. And then we at Clariant Power System Limited, we are working on two aspects of this renewable generation. And these two are very, very critical aspects. One is maintaining the voltage stability, and the other is maintaining harmonic mitigation levels as per IEEE norms. This maintaining the harmonics is challenging in a renewable environment compared to in an industrial environment. We have been maintaining harmonic levels in a comparatively easier manner for industrial sector because normally they have harmonics of lower range up to fifth, seventh. Most of the common harmonics are fifth and seventh. Then sometimes they go up to 11th and 13th. And then there is nothing above that mostly. So we have single tune filters available and just one or a combination of two filters we put and the entire thing is taken care and we bring it to the normal levels. And then on uh, LT side, load side also we have active harmonic filters, which also can be used as reactive power support. So they can do both the jobs. So with combination of these two or independently as a hybrid way or something, we can maintain easily the harmonic levels in industry or in maybe infrastructure sector and all. But renewable, they put a new challenge. They have harmonics ranging from low order harmonics up to 49th level or so. And mitigating harmonics of higher order is a challenge. So far, it was almost missing in the country because renewable was not there. So nobody was much worried about this. Some stray industrial plants need higher order harmonics. So there were some people who were able to give that solution. But today, this has become a very important, very common, and very, you can say, large requirement system is there for the harmonic mitigation. In fact, the capacitor industry has been surviving on most part because of this harmonic mitigation by passive filters for renewable sector. Otherwise, the capacitor uh, function has been taken over mainly by the SVGs, whether it is low voltage or medium voltage. So the capacitors are still required because in renewable sector, we can't manage without passive filters. Although there are active statcoms which can take care of some harmonics, but they can cater only up to small harmonic levels, maximum 13th or so. And we need to depend on passive filters. And passive filters here are not just single tune filters which we used in industry. They are high pass filters. High pass filters means we have another element, resistor, which is called damping resistor. And it has the capability to absorb harmonics of higher order. Suppose we design a harmonic high pass filter for fifth harmonic, it will mitigate not only fifth, but all the harmonics above fifth, say at least up to 7th, 9th, 11th, 13th or something, it will be able to mitigate comfortably. So we have one, say, high pass filter for lower order, and then we can have one high pass filter for a higher order, say 21st or so, which takes care of harmonics 21st onwards up to 49th. So their broadband mitigation is happening, and there are still some specific harmonics for which we have to have a specific single tune filter like second or third or maybe a 14th, 15th or anything as per the study report, whatever we get from the simulation studies. So this is how the harmonic mitigation is taken care. This passive filter is something which is sort of cannot be avoided, but we can always have a combination of SVG and passive filter, and in combination we can distribute some harmonics to SVG and some harmonics to the passive filter. But what we have to do is that 33% has to be taken care by the SVG, and for additional harmonic mitigation, if we want through SVG, we have to build into the extra capacity on that. As I said earlier, the gaps, we have to see that we don't have any gaps between the actual design and the execution. So we have to see that we get the right equipment, we get the right, you can say, experienced players who have successfully commissioned and all. And these things should be monitored not only after commissioning, but there has to be continuous monitoring. Otherwise, people just get away with commissioning and afterwards there is nothing. So there has to be continuous online meters and all, so that the people who are just fly-by-night operators, they are filtered out of the system. So what we see is that in India, we are able to from the very beginning almost, maintaining these standards and defining these standards, as well as you can say agencies have been lined up, they are trained. We have good consultants available, and these good agencies are there. And because of that, we are on the right track. And there are some hiccups, but they are manageable, and things will continue to improve. And we have seen just a small portion of the renewable growth. The major growth has yet to come in. Major growth has yet to come in means the major challenges also are still ahead of us. And we have to see that we don't falter in anything. Whatever deficiencies we have seen, we have to take care right now so that the future is safe and future is better for us. Thank you.